We have seen that mathematics can help us avoid drawing the wrong philosophical conclusions from Zeno's argument. An argument that invited us to consider infinite sequences of points and amounts of time. More precisely, an argument that invited us to consider points and amounts of time which one could enumerate in terms of the familiar sequence of natural numbers, the non-negative integers, 0, 1, 2, 3, and so on. And clearly it is good to avoid such errors. But by this we have not yet gained much insight into the concept of infinity itself. It is one thing not to draw wrong conclusions about certain infinite sequences. It is another thing to understand what we even mean when we call something infinite. As I said before, the set of all my kids is finite. It has exactly 2 members. The set of God's positive properties is perhaps infinite, and the set of natural numbers is definitely infinite. That's all very well, but what do we mean by that? And even prior to that, what do we mean by set here, as in the set of natural numbers is infinite? Let us turn to that question first. As a first approximation, think of a set as a list of items. The members of the set are the items on the list, and the set is the list itself. The only difference between actual lists and sets is lists are linguistic objects, something that we write up, while sets are not. And when we deal with a set, it is only meant to be important what is a member of the set and what is not, what is on the list and what is not. For instance, the set consisting of 2, 1, 3 is identical to the set consisting of 1, 2, 3. The order in which we list members of a set is irrelevant. It is only relevant that 1, 2 and 3 are members of the set and nothing else is. As you can see, we use these curly brackets to denote sets. The object mentioned in between the curly brackets are the members of the set. Accordingly, the set 1, 2, 2, 3 is identical to the set 1, 2, 3. It does not matter if we mention a member of a set twice or more often. It is only important what is a member of the set and what is not. By the way, also the set consisting of Hannes Leitgeb is a set. It is a set with just one member, that is, myself. So we can form sets not just of numbers, but of any kind of objects really. And a set does not need to have more than one member either. Furthermore, it holds that, for example, the set consisting of Hannes Leitgeb is identical to the set consisting of the philosopher who is giving this lecture. Since the set denoted on the left has precisely the same members as the set denoted on the right. We may even accept the existence of the empty set. Just think of a list without any entries. Accordingly, the empty set is a set without members, and it is the only set without any members. Because sets are completely determined by what their members and non-members are, and hence, if some sets X and Y both have no members at all, since they share precisely the same members and non-members, they must be identical. More generally, identities and differences of sets are meant to be governed by the following principle, which is called the principle of extensionality. For all sets X and Y, X is identical to Y, if and only if. For all Z, it holds that Z is a member of X, if and only if Z is a member of Y. Two sets are identical, if and only if they have the same members. If and only if means the same as is equivalent to. When one states an equivalence like that, one wants to say if what is stated to the left of the if and only if is true, then what is stated to the right of it is true as well, and the other way round. The left-hand side and the right-hand side are equivalent. Extensionality is just a more precise way of expressing what I meant before when I said it is only important for a set what is a member of it and what is not.